So let's go talk about systems. We were talking about momentum and systems of particles. And what we found here is that momentum is really a systemic parameter. So what we want to think about here is that momentum is best described by colliding objects. So what you want to do here is that suppose we have a system of particles where collisions occur. And so what we find here is that what I did last time is I probably set up some system here. Then I imagine that I have a system of particles. How big of a system? It doesn't really matter how big it is, but we could imagine that we have a system of particles like this. And these guys do collide and they move in a random way here. So what I've done here is I've defined a system, and in this system include more. So the net force on particles is composed of two types of forces. The forces are all the same, but maybe two categories.
Parabola. It's a little bit weird because this y isn't squared.
Hey, can somebody turn their mic off?
No?
Hey, can somebody turn that mic off, please? Thank you. So when we think about a net force, it's broken down into two pieces. One is external forces to the system. One was internal forces to the system. And what we said here is that by Newton's third law, that all internal forces will always cancel out to zero, no matter what. And the analogy that we gave here is, I think I said that probably pushing on my dad's dashboard. So you could imagine this is a dashboard right here. It doesn't have to be a dashboard. It could be a zillion other things. This is a dashboard in a pickup. And what happens here is that you could imagine that I take my hand and I'm applying my force on this dashboard. So then I have the force of my hand, and as a consequence, there's an equal and opposite force by the dashboard. So when I look at these internal forces, it turns out that the force of my hand plus the force of the dashboard, these guys will always sum to zero. And that's why all internal forces will never change the momentum of this thing. So only external forces matter in a system. So if I look at Newton's second law then says that the net force is then going to be the same as the external plus the internal, but we already said that that's zero. Only external forces can change the momentum of the system. So that implies only F external can change momentum of a system. But we've already dealt with that. We've already dealt with this particular case. And in this particular case, what we said here is that if we had an external impulse, that this changed momentum. So this is what we spent in the first part of the chapter here. Now, we only look at systems where there is no external force, there's no external impulse. And as a consequence, this tells us that the change in momentum of a system always remains zero. Now, if we think of this in terms of Newton's laws, applied to a system, then this is what we find here, is that if I have an external force that's equal to zero, then we say that the system is in equilibrium. And if it's in equilibrium, that means that the system is either in static equilibrium or the system is in dynamic equilibrium. So now I want to clarify this for where we're headed here. And here's what we're doing here now. So now I want you to think about the overall picture here. So when I think of momentum, so when we talk momentum, we need to think what is possible to measure and impossible. So what do we want to think about? So let me give you two examples just to try to really think about this strongly. Okay. So let's think about two examples. So here's example one. So remember, the momentum is a system parameter in general. So now what we want to do is that we want to imagine that we're going to be kicking a ball with our foot. So what happens when we kick our? Well, first I've got to draw a foot, which will be always fun here, right? I could imagine that, let's say I have a soccer ball. I'm not really sure how to draw, I don't know. How about, that looks a little bit too, that looks already funky here. But we could imagine that we got soccer spikes. And if we're talking about soccer, man, we probably have to think about Adidas. And what I'm imagining here is that I have a ball. So let's say that this guy is a soccer ball right here. So what we want to do here is that there's two viewpoints. right? So we have two objects. We have two objects, which then implies that there are two viewpoints. One is that we just focus on the ball, which is typically the most common way to do that. The other one here is that we focus on the system. So what do I know about this? Well, if I think about it, roughly the same way. So now here's what I'm thinking about. If I think about a single object, and in this case, I'm thinking about the ball. So what do I see here? I see the foot. Let me do a better job with the shoe this time. I don't know if that's any better here, but we need the stripes. And now I'm focusing on the ball. So what do I know about this situation? Well, I have my ball here, and what I'm thinking here is that I focus like this on the system.
Thank you.
My system is the ball. So what do I see about this? I see here that the foot is external to the ball. So when it's external, then that means when I come in and I kick this thing, right? If I apply a force here, this is an external force to the ball. And because that's an external force, the way Newton's laws tells us to think here is that now we apply the impulse momentum theorem and then say it is this impulse of the foot that has now changed the momentum of this ball. So if I think about a single object, I'm thinking about an impulse momentum thing here. So then I'm going to ask a question which will seem silly here. Do we worry about the foot before and after the kick? And the answer is hell no. We don't care about the foot. We always care about the ball. But this is not the system approach. So now, the other approach to this process, which is what we were talking about, there's two viewpoints here, is that if I have a system of objects, and in this case, this is the foot slash ball system. So now if I was to just copy this to be a little bit faster and then let me adjust it over here, right? So if I come over here, now I'm going to adjust this whole thing that we got going right here. Okay, so I'm going to come in here. I'm going to take everything off. So now I have the exact same situation, but now I'm coming in and I go like, oh, this is my system. And this system is quite different. So what do I know about this system? Here's what I know. I know that inside my system, there's going to be this force of the foot that kicks the ball. However, there's going to be an equal and opposite force of the ball kicking the foot. So what you're seeing here is that the foot is now inside the system. And because it's inside the system, and there are no external forces that we can see here, we then come in here and we say, okay, what's the net force? Well, there's no external forces, and we already know that there's no internal forces. So in this situation, the net force is 0 in each of these situations here. And as a consequence, this is 0. But wait a minute, we don't care about forces. What do we care about? We care about impulses. So the impulse of the foot plus the impulse, by the way, I was saying, I did not say this before, but the impulse of the ball, because these are all internal impulses, that equals 0. And this tells me about the change in momentum of the system. So when this is the case, what this really tells us is that we have to worry about the foot, because now the momentum of the system, if it does not change, right, this tells me that the momentum does not change. If it does not change, then the initial momentum of the system must equal the initial momentum, the momentum of the system in its final state here. And this statement, I would say, is the second fundamental law of physics. This is called conservation of linear momentum. The second commandment of physics, without any doubt. And so what is the second half of this course, this chapter, going to be? It's going to be about this tree, and this is a system. And that's what we want to focus on. So there's a lot here, okay? There is a lot to talk about. So what I'm going to do here is that I'm just going to summarize, because in Physics 4A, we will go into much greater detail here. So when we look at this thing, here's what we know. Conservation of linear momentum is about a system of interacting objects. And what I mean by interaction, that means that they are colliding within a system. From Newton's laws applied to a system, here's what we find here, is that if I have a system that is in non-equilibrium, let me step back here first. So from Newton's laws applied to a system, we focus on a singular point that represents the system. This is the center of mass point. Which in the past I've written as CM. So now we can look at the different situations of impulse or things or something differently here. If I have a system that's a non-equilibrium, okay, if it's a non-equilibrium, then that means that the net force on a system is not zero. So therefore, I have an accelerating center of mass location. So within that system, that means here that I have to look at what? That means I have to look at X center of mass, V center of mass, A center of mass. That's going to describe the system. In a very analogous way here, what this tells me here is that the impulse is also not zero. So therefore, this means that we don't talk about acceleration anymore. We talk about a change in momentum. So a change in momentum is the exact same thing as an accelerating system. And this is what we mean by the impulse momentum theorem. So when you use the impulse momentum theorem, it's because you have a system that is accelerating. Now we get to, and that's what we did in the first half of this chapter. Now we get to states of equilibrium. So very similar. So if I look at this in terms of Newton's laws, then I have an external force that is zero. And of course, if I have an external force, then the center of mass of the system is zero, the acceleration that is, which means here that I have a state of rest, which we call static equilibrium of the system. And then I have this velocity equal to a constant, which is what we call dynamic equilibrium. So then, what the hell does this mean? We focus on equilibrium states when dealing with conservation of momentum. So if you say the word conservation of momentum or you say the word equilibrium for a system, they mean one and the same thing. So what do we know here? And this is where I don't want to really spend very, very much time on this thing here. So if we are in a state of static equilibrium, what does that mean? That means that the center of mass location does not change before and after some interaction. Okay, it does not change. Let me give you an example here. And again, I don't want to do this very much. So imagine that we have a boat. Okay, so we have a single person in a boat. So imagine that here's my boat right here. And then, of course, the boat is in water. So when I'm thinking of my boat here, the thing that I want to think about is that I got to think about the center of mass location. So it seems here like somewhere around right here, that would be the center of mass of boat with nobody in there. Now, if I now take a person here, right? And here's our orange person right here in the boat. Well, that person is going to do what? It's going to move the center of mass between this person and the center of mass of the boat. Okay? So what do I mean by that? No, an internal force cannot change the center of mass. And it cannot change the momentum of a system. I'll get to that right now, Michael. Okay? It cannot do that. So what I'm going to say here is that this right here, along this green line, is going to be the center of mass of system. Okay? That's the center mass of the system. Now, to try to make this a little bit more clear, let's say that over here is the shore. Okay? So I have a shore right here, and we could say that we're measuring the distances from there to there. So you know what? I got to move this over. So let me move this over here. Now, I don't want to make this too tricky, but here's what happens now. So I look at my system. So what's going to be my system here? My system here is going to be the boat plus the person. Okay. So when I look at this thing, I see that there are no external forces. There are no impulses here. They're equal to 0. So this tells me that the center of mass before has to equal the center of mass afterwards, because none of the objects are moving within the system. So now what we're going to see here is that this person gets up and moves now. So this person now moves to the left end of boat. Okay. So what do I know here? Well, I have my water, right? And of course I have my shore. And what we're seeing here is that all I know is that the orange person has moved. So note, as the orange person moves, that means that the center of mass of, let me be careful here. as the orange person moves, the locations of the person and boat must rearrange themselves to keep X center of mass equal to a constant. So look what happens here. So if I now look at the boat, here's what happens to the boat. I gotta change this here. So what I'm trying to show you here is two things here. The orange guy is now over here. And what happens here is that this is still right at the center of mass. So as the person moves this way, in order to conserve the same center of mass, the boat must move in that direction. In other words, the boat moves closer to shore. So that means the center of the mass of the boat may be over here, but this center of mass of system does not change. So if this is the center of mass of the system here, and this is before, then this distance from here to here, center mass of the system afterwards, they have to stay the same. That's what we mean by static equilibrium in systems. The center of mass of the system does not change, which is kind of wild when you think about it. So now, let's go look at this guy again now. So now, there's a second piece of equilibrium. There is dynamic equilibrium. And this is what we're most interested in this course. If we have a dynamic equilibrium of a system, it says here that the center of mass velocity does not change before and after some interaction. And typically when we say interaction, we mean a collision. So in other words, conservation of linear momentum implies that V center of mass remains constant before and after a collision, because it's in a state of dynamic equilibrium. And here's the crazy thing. Look what I said over here. If the orange person moves, the locations of the person and the boat must rearrange themselves to keep V center of mass fixed. The definition of conservation of momentum essentially says this, that the individual momentums of a system must adjust themselves, let me be careful, must readjust themselves to keep the center of mass equal to a constant, which is equivalent to the total momentum of the system being a constant. This is what it means to be conservation of momentum right here. This is the physical meaning of what it is. So now let's try to draw some pictures. So here's an example. And this is a hard thing for me to draw, so I'm not really sure how I'm going to do this, but I imagine that I have a situation that it's before a collision, and then I'm going to have an after. And then, of course, I'm going to separate these two situations. So what I'm going to see here is that I imagine that I have a surface, and we want to make sure that the surface is frictionless. And what I'm going to see here is that I have a block coming in. In fact, I think I'm going to draw them a little bit bigger. How about if I draw them like this? And then I'm going to have another block right here, which is larger. So I think I'm going to color code these guys. Okay. What I'm going to do here is that I'm going to call this block 1, and I'm going to call this block 2. And I think what I'm going to do here is that I'm actually going to copy this and bring it over here. So you could see that before and afterwards. So now I'm going to look at the detail of this thing here. So what I need to do here is that the first thing I need to look at, what is the center of mass location of these two objects? Well, the center of mass has to be in between block 1 and block 2. And I would say that the center of mass would be right here. In fact, I'm going to draw this in red. So the center of mass is closer to 2 than 1 because block 2 is larger. So now, here's what I'm going to do now. I'm going to say that this guy is moving with some momentum P1 initial. And for the sake of argument, I'm going to say that P2 initial is at rest. So now what happens here? Afterwards, wait, before I move. So this guy here is the center of mass location. So what does this really tell me right here? So because the blocks are moving, let me go all the way across. Because the blocks are moving, the center of mass location must also be moving. So in this case, if the center of mass, because the green block is moving to the right, then I have a center of mass velocity that's moving in that direction. So what conservation of momentum says here is that this center of mass afterwards is still the same after the collision. In other words, even though block 1 might be headed in this direction, and block 2 might be headed in that direction, that center of mass continues to move to the right. So dynamic equilibrium for systems implies V center of mass before must equal V center of mass afterwards. That's what it means to be in dynamic equilibrium. So to get a sense of what this might look like, we also say that dynamic equilibrium of systems is on one-to-one footing on conservation of momentum, linear momentum, that is. And conservation of momentum implies that the total momentum of the system has to equal a constant, and it cannot change. So if I now focus on my system, you can see here that there's my system right there. And when I look at the system, I'm going to say that there are no external forces because it's in dynamic equilibrium. So if there's no external forces, then we can come over here by conservation of momentum and say, so if there's no external forces, then the change in momentum of the system cannot change with time, and therefore the momentum of the system before has to equal the momentum of the system afterwards. That's what we mean by total momentum conserved. So if I now look at this as a bar diagram, you could imagine the following scenario here. So now if I have a momentum bar diagram, then here's what I find. This is the total momentum of the system beforehand. So I have one initial momentum, and that's of the block right here. When I look at the momentum of block 2, it has no velocity. So this thing is 0. So according to conservation of momentum, this line right here represents, assuming that this line here is 0, this represents that the total momentum of the system is a constant, and therefore it cannot change. So now if I look at this guy, if I choose this guy over here to be positive, let's say that this direction right here is positive, this direction is negative, you could see that after the collision, P1 is going in the negative direction. So let's say that P1 is now this big after the collision. And you could see that it's below the axis. So now what I want to do here is that I want to come in and I really want that image that we used before. Okay, so the way I want to look at this guy is that I don't know how to really show you this any other way, but I'm going to go back to here. Now, this is from the impulse momentum theorem. So what do we know here? What's the first thing that we got to do here? Is that momentum has to be conserved. So one things that we've done in the past here is that we could imagine that this is the ball coming in, it slows down, and then it stops. So when I look at the momentum of 2, I still have to have a positive. So the first thing this guy has to do here is that when there's a collision, you have to stop block 1 because it's going to change direction. So what am I doing? I got to stop block 1. So therefore, I have this amount of momentum that's going to stop the block, right? So look what I'm going to do. I'm going to put lines here, and this is the momentum transfer required to stop block one, just like the baseball and the bat. So now what happens, right? So here, what you're seeing here is that in this situation, we slow down and stop. But now what happens? We speed up here. So when you look at the momentum of the block afterwards, it's going in the opposite direction. So now I have to account. Note that right now, that little green P1 is negative. So I have to add another block on top. And then this piece right here, as you can see here, that little piece here, this is the momentum transfer to speed up block one. And this is what we call the final momentum of block two. And so what are you seeing here? Here's what you're seeing. These momentums after the collision must readjust themselves to conserve total momentum. So if I look at before the momentum, the total momentum is the same as the green bar, but afterwards, the blue and the green have to readjust themselves to make sure that the total momentum is a constant. This is the same thing as saying that V center of mass is a constant, that the system is in dynamic equilibrium. And here's the crazy thing, which is hard to see. We'd have to get in and actually look at numbers in great detail, which I won't do this semester, but in 4A, we will definitely do this. And here's another thing. There is an exchange of momentums during a collision. In other words, the momentum of P1 initial goes to P2 final, and they are literally exchanging and P1 final. So there is an exchange of momentums. And I will try to explain this right now with examples.